And we'll get Martin Davis, my colleague, who's going to give us a little talk about some of the games he's been playing with SVG. Nothing but pretty pictures for the whole half an hour, I understand.
There we go. Yeah, let me just share my screen here. Is that the one? There we go.
That's a winner.
Okay. Well, good afternoon, evening, middle of the night, everyone. Thanks for hanging out to the end of PostGIS Day. Hopefully this is a little bit of a lighter talk to finish up the day with. I'm going to talk about how to generate pictures from PostGIS right out of the database. And there's a little bit of a change from the talk synopsis. The pattern part is actually going to be some cool geometric patterns that we could look at. And that'll be at the end of the talk. So I'm Martin Davis. I'm a geospatial engineer at Crunchy Data. I've been a developer for about 20 years on the JTS topology suite, GEOS, PostGIS, and most recently PG-svg. So my particular interest is in math and geometry and making them better and looking at them. So, of course, the great thing about spatial data is that we can look at it. We can display it as graphical images in 2 or more dimensions. There's, as we've seen in all these talks, there's lots of different tools that you can do that with out of PostGIS. You can use web mapping engines such as GeoServer or MapServer. You can use external applications such as QGIS or PG-admin. You can produce geospatial vector formats such as MVT or GeoJSON, in which case to visualize those, you typically need some kind of web map library like MapLibra. Or you can roll up your sleeves and dive into a programming language and find a graphics API and a driver for PostGIS and probably a spatial API, and then you can start creating images. But as we've heard in quite a few of these talks, what's really nice is when you can do everything right in the database. So PostGIS native. And so how can we generate images out of the database? Well, there's a way, and it's called SVG. And for those of you, anyone not familiar with SVG, it's scalable vector graphics. It's a W3C standard. It's a language for defining 2-dimensional vector graphics. And it's XML markup based. So it's about 20 years old, but it's now implemented in pretty much all web browsers. It has all the goodies that you expect from web things, like uses CSS styling. You can embed it in HTML pages. You can make it interactive using JavaScript. It's dynamic, so you can change the images. And you can also edit it. And a really good tool for doing that is the open source Inkscape editor. So what does SVG look like? You can see a simple little SVG document here. You've got the SVG tag that indicates all the content is SVG. You've got a view box attributes, which specifies the area that is going to be displayed. There's, in this case, there's a graphical element, the path element. And it has a few attributes that control what it actually ends up displaying. There's a fill rule, which in this case says we're going to display a polygon. There's the CSS styling that indicates the fill and the stroke. And then there's these drawing commands, which actually specify the coordinates that get drawn. So fairly simple, but still takes, there's a bunch of fiddly details here. So in actual fact, PostGIS has had an ST as SVG function for a long time, but it only produces the drawing commands. So there's a lot left that needs to be added in order to make an actual SVG document that can be displayed. You can, of course, add all that using SQL concatenation, but that gets pretty ugly. You can see it's really fiddly and it's error prone. In fact, there's an error in that statement. See if you can find it. So that's really a non-starter. So I've been working on a little side project called PG-svg. And what this is, it's a PG SQL function library. It's essentially a domain-specific language embedded in SQL for generating SVG documents from PostGIS geometry. PG SQL is actually nice for doing that because it has things like name parameters and variadic arguments, which make for really nice function signatures. So the functions produce the text for SVG elements and attributes. There's functions for generating shapes, such as SVG shape and SVG polygon. There's functions for doing styling, and then a function called SVG doc that wraps all that up into the document that you can then produce from your SQL statement. So the library's on GitHub. It's just a simple file that you can load into PostGIS. You can check it out there. Let's have a look at an example, simple example. This is going to display a Delaunay triangulation generated by PostGIS. So you can see the first select statement there, which creates Delaunay triangles using a PostGIS function, turns them into SVG, and styles them with a set of CSS properties for fill and stroke. The next select does the same thing for the original points, because we want to show the points on top of the Delaunay triangles. And then finally, we use another select to which we aggregate all the SVG text produced by the previous selects into an array, and we pass that to the SVG doc function. And we also give that a view box. And in this case, we generate the view box from the actual extent of the original geometry. But you can actually generate it in any way you want. It could be fixed or however you want to do that. So then we can run that code just using PSQL. To do that, we can use a couple of PSQL options to ensure that all we get out is the actual SVG text. And when we run that code, you can see the text that's output on the left there. You can see that's the SVG document containing all the paths for the triangle polygons and the circles to indicate the points. And they're styled according to the styling that we gave it. So let's look at a slightly more complicated example. This one's called Howell's SVG. And it's going to run 3 different PostGIS functions, one for convex hull, one for concave hull, and one for the maximum inscribed circle. And we're going to render the maximum inscribed circle using the buffer function. So we convert all those to SVG and gather them up like we did before. And that's what we wind up with. So, of course, what people really want to do is display maps using this, and that works really well. Here's an example of a map of US high points. It shows high point data for states represented as triangular polygons, and the height of the triangle is proportional to the elevation of the high point. The fill color also represents the elevation of that high point. This is one of the things about producing SVG in SQL is that you can drive the styling off the data in your using your SQL. The base map is produced using natural earth state boundary polygons, which have been filled with a linear gradient, and we've added the state names on top of the polygons. So I'll just show a couple of SQL snippets there to show how this works. The linear gradient is actually what's called a SVG definition. And it's used as the fill property by referring it to the URL. So we can define the fill using the URL, and then we can include there's a SVG linear gradient function which produces the markup for the linear gradient, and that's included in the SVG document. Here's the SQL that actually generates the high point symbols. So you can see we're computing the height of the symbol based on the high point elevation and computing the color based on the height. And then we actually create a polygon directly. In this case, we're not using a PostGIS polygon. We're actually passing computed points to an SVG polygon function. And here's the full map. So you can see the difference in the symbols really represents the topography moving across from the mountainous west over through the plain states. The Appalachians are a bit higher, and then dropping down to the coast in the east. Here's another example of a world map, also using the natural admin boundaries. Now, a world map obviously is fairly large, but we can reduce the data volume by using the st-snapped-grid function. We can generate a geodetic grid using a simple generate series function. We can transform that all to the Robinson projection. And then we can style the countries with a fill using a set of hues based on the country continent, and then dithering those slightly by using random values around the main hue. And here's what that looks like. So you could generate this SVG and embed it in web pages. The SVG actually has titles associated with the polygons, which show up on hover. And you could also attach IDs to all the shapes so that you could use that to drive other things on the web page. So, so that's the serious part of the talk. Now we're going to get into patterns. And those are more purely mathematical images that you can compute using SQL and then display using SVG. So we're going to look at, the first thing we're going to look at is the fractal or fractals, and the fractal that everybody knows about is the Mandelbrot set. So this is a fractal that fills the XY plane. It's defined as the set of complex numbers for which a simple function diverges or doesn't diverge when it's iterated. And this is a classic example of using recursive CTEs in SQL. But those examples usually produce ASCII art, which is pretty ugly. So using SVG, we can do better. Instead of producing text symbols, we're going to produce SVG rectangles and then style them with an appropriate color palette to produce an image like you see. Now, one issue is, in this case, we're looking at a 400 by 400 grid. So that's 160,000 rectangles, which is a little much for a browser to handle. So we can actually reduce that by using run length encoding, using another set of recursive CTEs to do that. And that gets it down to about 12,000 rectangles, which is easily displayable in a web browser. So I'll show the code here just to show that it's not too much code. The initial part of this is all one SQL statement. The initial part of it is the recursive CTE to actually compute the Mandelbrot set function and determine where it diverges. And then we're going to determine the number of iterations before divergence, and that's what drives the styling. Then we have a couple more CTEs to scan over all the cells that we computed and turn them into runs of cells that have the same count value. And then finally, we're going to create the SVG. We're going to assign a color value to each one of the rectangles based on the count. And then we're going to generate an SVG rectangle with the appropriate width and position, and then output that as an SVG document. So another fractal example is a Hilbert curve. This is a space filling curve, and it's actually used inside PostGIS. It's actually how, when you order geometries in PostGIS, they're actually ordered based on the Hilbert curve. We can generate the actual graphic for the Hilbert curve using something called a Lindenmayer system, which is a set of recursive rewrite rules that produce Turtle Graphics drawing commands. So there you can see the rewrite rules. And when we iterate over those, we produce a set of drawing commands to whatever resolution of curve we want. And then we can turn that into SVG code, just like we have done with the other examples. We create line segments for each one of the line segments generated by the drawing commands, and we assign them colors. In this case, we're using a spectrum across the curve, which helps to show one of the nice properties of the curve, which is that when things are close in space, they tend to have a similar color. That means the curve has good spatial locality, which is why we use it for ordering in PostGIS. Here's the SQL for that. Here's the code to evaluate the L system as strings. Then we interpret that drawing string to create lines. And finally, we create the SVG by converting each of the lines to a SVG shape and assigning it a stroke with the color value chosen from the spectrum. Here's another kind of fractal that you can also generate with an L system. It's the dragon curve. I won't show the SQL for that one, but you can get all the SQL for these demos in the PG-svg repo on GitHub. So my final set of cool geometric demos is tilings. The first of these is Penrose tilings. The Penrose tiling is an aperiodic tiling of the plane, which means that it's a tiling that never repeats. It's generated by using these two rhombic shaped tiles here, and with certain adjacency constraints, so that that's what ensures the tiling never repeats. And there's a technique called deflation that lets you generate these tilings. I won't show the SQL for this. You can see it on the repo, but it's the same kind of thing. It's a couple of CTEs to actually generate the tile shapes, and then calling the SVG functions to output them as SVG. And finally, there's another kind of tiling called a Trichet tiling, and that's made up of random placements of these two types of tiles you see here with the quarter circles on them. Now, the nifty thing about doing this in PostGIS is that we can generate a random set of those tiles as lines, and then we can use PostGIS to merge the lines together. And then when we color the lines in SVG, you can start seeing the sort of long runs of this that are all one single line. Or we can use SD polygonize and convert those lines to polygons and then fill the polygons. So again, you can see the long squiggly polygons generated by this. And I think these images look pretty cool, actually. So that wraps up my talk about generating SVG from PostGIS. I think there's lots more that can be done with this. Some more functions to generate different kinds of SVG elements, more symbols for doing charting on top of maps, SVG for legends and map surrounds, potentially embedding images from PG raster, perhaps providing SVG for non-spatial charting. I think that could be really interesting. And then also something I've got running is being able to produce SVG directly from PG-svg. So the idea is there is that you can write a function that'll produce SVG, and as you see, it can be as complicated as you want. And then you can make with one call to PG-svg, you can deliver that SVG into a web browser. So that's it. I'd be happy to answer any questions.
So we were talking earlier about the place of SVG in the web mapping world, and I was wondering, is SVG yesterday's technology?
No, I think it's actually got a lot of utility if you're wanting to make simple thematic maps. It's just such a simple stack. You can just dump SVG into a web page and you've got a map right there. So you don't need, it really reduces your stack to almost one component.
So yeah, so for the embedded map, the live embedded map, it becomes easy to make a web service that just dumps out something that can sit inside the web page. And I guess it has the advantage of then being CSS stylable.
And also interactive with JavaScript. So you can easily make a very interactive map page with a bit of simple JavaScript.
Yeah. So not so much a web mapping trick as a small map generator.
Yeah, maybe we need another term to describe that.
Yeah.
Simple
maps. Does anyone else have questions?
Everyone's burned out.
Yeah, well, it's been a day. It's been a bit of a day. Yeah, I've been up since 4. Oh yeah, so Josh Clark asking, have you thought about animations with SVG?
I've certainly thought about it, and obviously it's really possible, and SVG's got some animation facilities built right into it, and then you could also animate things just using JavaScript. Yeah, make some demos.
Yeah, so what kind of animation does SVG have built in?
Well, I just glanced at it briefly, but there's a few tags and properties that let you define animations. So to be honest, I haven't looked at it in depth, but put it on the to-do list.
Yeah, so you can say from here to here over this time frame.
Yeah, I think so. Yeah,
it will handle all the transitions for you.
Yeah, exactly.
Yeah. Well, I can see some potential small map uses for that as well.
Absolutely. Yeah, the sky's the limit with this stuff.
Okay, so we have, oh, there's one more. Can SVG be interactive? Well, SVG be interactive?
Yeah, we just been talking about that. I mean, you can, it responds to mouse events and hover events, just like HTML does, and you can tie JavaScript to that and use that to change other things on the web page. And then you can use JavaScript to change the SVG on the fly too.
Yeah. The extent to which the individual objects in the map are just co-equal parts of the web page is sort of the big differentiator between SVG sitting in your web page and some fancy map frame like a Mapbox frame.
Exactly. Working with the grain of the web.
Yeah, within limits.
Yeah.
Yes, Josh. In theory, we can make a whole UI this way. Just remove the middle tier. So why can't we do that, Martin?
Hey, let's do it.
Yeah.
I mean, it's worth pointing out that originally some of the map frameworks used SVG to draw their vector features on maps. Like I think OpenLayers worked like that originally. So there's a lot of power in there.